Hi, everyone. My name is John He, and I'm going to show you today a record of the birth of the East Antarctic ice sheet 34 million years ago. This was a critical moment in the planet's transition from a greenhouse to icehouse world. But instead of looking at the climate or cryosphere record itself, I'm going to show you how we can extract information from the solid Earth beneath the glaciers as the cryosphere expanded and incised into the bedrock. So this talk is about visualizations, but let's start with a very simple representation of the importance of the interplay between climate, cryosphere, and the solid Earth. When we hear about climate change and melting ice sheets, we commonly think about these first two parts, the warming climate and melting glaciers. For example, higher global temperature and CO2 drives ice sheet decay, and in turn, this could decrease the reflection of solar energy and further drive temperature increase. But another important part of this equation is how the cryosphere itself impacts the subglacial topography by incising and eroding into it. In turn, the change in topography affects how ice sheets grow or shrink, where they grow, and in some cases, limiting their growth or exacerbating their collapse. And this is the part that I want to focus on today. How does the growth of the ice sheet impact the crust? How do we go about doing that? Well, in the realm of climate and the cryosphere, we can go look at the sediment archives and isotopic records, which tell us about change in temperature, carbon dioxide, and global ice volume. An example of this is the Zako's curve pictured on the lower left. What about the crust? How can we figure out what happened more than 34 million years ago in the subglacial topography? One way that many previous researchers have relied on is to take the total volume of sediment and in set intervals, restore the volume via the current erosional pathways to the landscape, step by step. But that's very indirect and relies on a lot of unknowns. What we want and what we're after here is a direct way of constraining changes in the subglacial topography going back tens of millions of years. The answer to this is thermochronology, which is a broad suite of methods and tools that allow us to determine the time at which a rock sample or crystal dropped below a certain temperature. There's a lot of complexities in that, obviously, in getting from individual time temperature data points to a picture of how the paleotopography changed. So in the rest of the talk, what I'll try to show you is how we can get from the raw data pictured here in the upper right to an interpretation of paleotopography that varies in time and space. Before I get started, let me just briefly introduce what thermochronology is if you're unfamiliar with it. So as a glacier erodes surface material from the bedrock, the rocks beneath move up towards the surface and cool. Radiogenic isotopes only begin to accumulate below certain temperatures. We call this a closure temperature. In the case of low temperature thermochronology, helium is produced as a daughter product from decaying uranium. So by measuring how much helium and uranium is in a crystal, we can record the time when a rock dropped below the closure temperature, which is when they come up to 2 to 3 kilometers of the surface in the case of apatite helium thermochronology. Of course, if we can sample every square kilometer of an area and get data sets that evenly cover a spatial extent, then we can get a good idea of the topographic evolution. But as you can imagine, in Antarctica, almost everything is covered by ice. In fact, to get to these outcrops, a helicopter and the assistance of a mountaineer was necessary. So how can we get from time temperature data that comes from these microscopic crystals at these limited cliffs and outcrops to a picture of regional topography on the scale of many kilometers? Well, first, it involves a lot of rock crushing and frustrating hours trying to pick up microscopic crystals with tweezers, and some hours of laser heating and mass spectrometry. But long story short, what we get at the end is a large data set of many, many individual ages. You see that on the left figure, and conventionally, we're interested in the age elevation relationship on a vertical transect. So we get data from as close to a vertical profile as possible and try to see how the thermochronology age on the x-axis changes with the depth or elevation on the y-axis. But how do we account for the complicated topography from which each data point was sampled? And you can see from the animation here that the samples come from a pretty large area in East Antarctica. And this is not quite the same as a simple plot in 1D, where we only think about the elevation of the sample. This is where data visualization becomes important. And the first step we do is to consider the data set in terms of schematic and member scenarios to understand the spatial temporal variability in the crustal temperature profile. What's illustrated here are different scenarios for how we can interpret the same data differently, depending on different assumptions about the paleotopography. I'll zoom in on some of these in a second to explain them in a little more detail. But in general, I want to point out that we're imagining a block of crust from a stationary reference frame. That is to say, as a glacier erodes the surface, the topography and surface elevation will continue to drop, but the blocks will not move in these figures. So the initial topography is the dashed surface at the top. And as the topography evolves and drops, the paleoisotherm also evolves accordingly. And these are the red surfaces, and they're essentially contours of constant temperature. Zooming in on the top two figures, in the first case on the left, there's significant topographic relief prior to the time interval we're interested in, which is the Eocene and Oligocene transition 34 million years ago. This topographic relief represents a steep fluvial valley or pre-existing glacial valley, and everywhere in this block, the surface is being eroded at the same rate. So exhumation is spatially homogeneous because the topography is the same before and after. In the second case on the right, the topography at the beginning is rather flat. There's no major valley. But as the surface is eroded, a trough is being incised so that the corner of the block that's closer to us is eroding much more quickly. We need to pay attention to these assumptions because we're trying to extrapolate from two sampling transects to the whole area. And each of these scenarios considers how our constraints on the magnitude of erosion during this time are affected by changes in relief. We also consider how the timing of tilting could affect this because we know that a regional unconformity in this area is tilted. And what you'll notice is in these figures, the top surface represents the closure isotherm at T1, the time at which the topmost sample came close enough to the surface for the thermochronology clock to start ticking. And the bottom surface represents the time at which the bottommost sample came close enough to the surface. So the top and bottom red surfaces. Suppose the top sample crossed the isotherm 35 million years ago and the bottom sample crossed it 34 million years ago. Then in the first scenario, that's only 1.4 kilometers of erosion in a million years. But under different assumptions, in the bottom right diagram, that implies 2.6 kilometers of erosion in the same period of time from the same data. In short, these diagrams can help us visualize the spatial complexity of thermochronology data and figure out how best to interpret the data set. The second part of the analysis is then to move from these schematic diagrams to a full 3D thermokinematic code. This uses the PQ modeling software developed by Jean Braun. And basically it takes a crustal block with defined topography and calculates the thermal profile of the crust as erosion takes place. Here, each dot at the surface represents a hypothetical sample and its thermochronology age. When we remove the top surface and the grid of samples, you can see beneath the surface as well. These are the isotherms of constant temperature. And we're interested in the shallowest layer here in blue, which is the closure isotherm. And you can see the isotherm is warped, just like topography. And we use these synthetic models to help interpret the analytical data. By inputting different scenarios with different timing rates and other parameters, we can compare the expected thermochronology ages with each of these scenarios with the spatial data that we actually get. Finally, the third step we can take is to run the model in inversion mode. What this means is that we give the model the data set that we have and ask the model to find the best fit parameters that matches the data. To do this, we use the parallel computing capabilities at the University of Arizona High Power Computing Center. And the code runs tens of thousands of different scenarios. The figure on the right shows our model run with the misfit to data on the y-axis, the number of iterations the model has run on the x-axis. Each point in this figure is a single 3D model like the previous animation or the 4 animations on the left. The inversion run first starts with some random parameters and over time gradually selects the better and better models and hones in on the best fit. The results can then be visualized in the full set of parameter space. So if I ask the model to find 6 unknown variables, that's a 6 by 6 grid of all the possible combinations. And in this example, the 6 variables are total relief change from beginning to end, and exhumation velocity or erosion rate at 5 different time intervals. But other variables that we could also ask include changes in the geothermal gradient, changes in relief from any time intervals, and we can also increase the number of time intervals. So this very rapidly becomes too much to handle and hard to visualize. Taking the same information from the multi-parameter space, I've visualized some of the parameters here in 3D to more intuitively show the results of the inversion runs. On the y-axis is relative misfit to data. So the top peaks here in red are the best fits. Each of the time varying parameters are then stacked along the z-axis on the right, and the y-axis in front is exhumation velocity. So the topmost surface here with the red line is essentially a time versus velocity plot of the best fit model. And what we end up with are a lot of ways looking at the same data set. The schematic data sets are important to start with so that we can properly investigate the numerical models and the large data modeling runs, so we can evaluate the information that the computer spits out. Does this best fit model actually make sense? Is it meaningful? And does it correspond to what the samples actually say based on what we know from the schematic diagrams? And finally, to bring it back to tangible reality, what does this all tell us? At the end of the day, we're interested in the topographic evolution of Antarctica more than 34 million years ago. The steps I showed just now illustrate some of the complexities of acquiring that information. There's so much that we don't know, and we need much more data to get a full picture. What we do know from the data is that around 34 million years ago, at least 2.6 kilometers of erosion occurred in a very short time interval. This was a warm transitional period when glaciers were first starting to form, when it was still much warmer than the frigid Antarctica today. Today in Antarctica, the summer temperature typically does not fall below freezing. So with warmer temperatures back then, basal melt rates of glaciers increase, and this means that beneath glaciers, meltwater can flush sediment and drastically increase erosion of the bedrock. We know this to be true from glaciers with temperate thermal regimes around the world today, like in Southeast Alaska and Patagonia. But it's particularly exciting to find direct evidence of this in the geologic record, that around the time of the Eocene-Oligocene transition, there was a major period of rapid erosion. Thermochronology datasets like this are essential for understanding how topography have evolved in the past and will evolve in the future. They're therefore essential for simulations of ice sheet stability and, more importantly, instability. With more and more data, we can then begin to draw links between the thermochronology record and the climate and cryosphere record and get a better understanding of the interplay between each of these components of the complex system that is the planet's surface. Thanks for listening.